Good evening, my name is Pablo Sevilla. I am an Erasmus student from Mechanical Engineering and my project is about reviewing criteria of material effort. The risk of a fracture at certain point of a body is defined by the totality of the unit elongation in all directions that pass through the said point, or shorter, strain of the element of the body define its material effort. To determine the material effort of the element of the body, it is required in general to give 6 independent quantities that describe a uniform strain, 3 elongations, lambda x, lambda y, and lambda z, and 3 angles of shear, sigma s, sigma y, and sigma z, in the direction of the Cartesian coordinate axis. If x, y, and z have the same direction as principal elongations, lambda 1, lambda 2, and lambda 3, then lambda 1 equals lambda x, lambda 2 equals lambda y, and lambda 3 equals lambda z. Sigma x equals 0, sigma y equals 0, and sigma z equals 0, which means that 3 principal elongations are sufficient to define material effort in uniform strain. Thus, a certain function sigma of principal elongation and angles of shear in arbitrary mutually perpendicular directions would be a measure of material effort. Since every state of strain is related to a uniquely defined state of stress of the said element, sigma is also a function of 3 principal stresses, V1, V2, V3, or respectively normal, Vx, Vy, and Vz, and shear sigma x, sigma y, and sigma z. Probably the most long-standing issue with failure criteria is whether they should be expressed in terms of stresses or in terms of strains. The discussion goes back to the very beginning and continues even now. For example, some aerospace organizations specify design procedures in terms of stress, while some others use strain. Typical technical exchanges on the subject remain inconclusive. Still, the uses of failure criteria are manifold, and everyone is left with the problem of making the best possible choice. Kinds of stresses. Mises and Tresca failure criteria. The main interpretation of the Mises criterion is that it represents a critical value of the distortional energy stored in the isotropic material, while the Tresca criterion is that of a critical value of the maximum shear stress in the isotropic material. Historically, the Tresca form was considered to be the more fundamental of the two, but the Mises form was seen as an appealing, mathematically convenient approximation to it. Now, both are usually started side by side with little or no preference. Drucker-Prager failure criteria. The Drucker-Prager yield criterion is a pressure-dependent model of the determining whether a material has failed or undergone plastic yielding. The criterion was introduced to deal with the plastic deformation of soils. It and its many variants have been applied to rock, concrete, polymers, foams, and other pressure-dependent materials. The Drucker-Prager model has been used to model polymers such as polyoxymethylene and polypropylene. For polyoxymethylene, the yield stress is a linear function of the pressure. However, polypropylene shows a quadratic pressure dependence of the yield stress. Failure criteria. The Moore-Coulomb failure criterion is a set of linear equations in principal stress space describing the conditions for which an isotropic material will fail. With any effect from the intermediate principal stress sigma 2 being neglected, MC can be written as a function of major sigma 1 and minor sigma 3 principal stresses, or normal stress sigma and shear stress tau on the failure plane. When all principal stresses are compressive, experiments demonstrate that the criterion applies reasonably well to rock, where the unaxial compressive strain C0 is much greater than the unaxial tensile strength T. C0 divided 10 is bigger than 10. Some modification is needed when tensile stresses act because the theoretical unaxial tensile strength T0 predicted from MC is not measured in experiments. The MC criterion can be considered as a contribution from Moore and Coulomb. Moore condition is based on the assumption that failure depends only on sigma 1 and sigma 3, and the shape of the failure envelope, the loci of sigma tau acting on a failure plane, can be linear or non-linear. Coulomb's condition is based on a linear failure envelope to determine the critical combination of sigma tau that will cause failure on some plane. A linear failure criterion with an intermediate stress effect was described by Paul and implemented by Meyer and Labus. Mises and Tresca failure criteria. The main interpretation of the Mises criterion is that it represents a critical value of the distortional energy stored in the isotropic material, while the Tresca criterion is that of critical value of the maximum shear stress in the isotropic material. Both criteria are widely discussed in many places. Historically, the Tresca form was considered to be the more fundamental of the two, but the Mises form was seen as an appealing, mathematically convenient approximation to it. Now, both are usually started side by side with little or no preferences. The two criteria are specified below in principal stress space. Both are one-parameter forms, specified by either the unaxial tensile strength T with Z equals T, or the shear energy is shear strength S. Mises criterion, critical distortional energy, the equation of a top, where C equals to T and S equals to T and square root of 3. Tresca criterion, critical shear stress, the equation which is in the bottom right of this slide. Then the three separates form above out of the maximum shear stresses in the three principal planes. Both of these single property criteria can be calibrated on either T or S. And two figures below for biaxial stress states calibrate both criteria on T and then on S. Calibration on T is the image of the top left, and calibration on S is the middle bottom picture. Which procedure is better grounded, calibrating on T or calibrating in S? Which criterion is more physically relevant, Mises or Tresca? Calibrating on S might seem more logical because yielding is caused by distortional, not dilatonial states in ductile materials, and distortion more nearly and easily associated with shear stress rather than with unaxial tensile or compressive stress. With calibration by T giving case 1, there is still the choice between the Mises and Tresca forms. Mises is smooth, while Tresca has corners. At the crystal level, single grain yielding does associate with dislocation movement of slip planes. This is caused by shear stress on the slip system resolve shear stress. It would be tempting to say that this justifies and validates the Tresca criterion. But that is only part of the consideration. The condition of isotropy implies and applies to polycrystalline aggregates with individual crystals taking all positive orientation. Dislocation included plastic flow occurs over many slip systems. Furthermore, dislocation pileup occurs at the grain boundaries. The vastly more complex behavior at the aggregate level compared with the crystal level must involve averaging over a wide variety of physical conditions and effects. This averaging has a smoothing effect that is much more supportive of the smooth Mises criterion than of the non-smooth Tresca form. Even though the maximum difference between the Mises and Tresca criteria is only about 15%, this difference represents a symmetric error divergence of the part of the Tresca criterion, and it should not be used for any isotropic materials, even for ductile materials. It is inappropriate to place the Tresca criterion on the same level as the Mises criterion, as is done in most tutorial works. The Tresca criterion merits only an historical reference. This is considered with the fact that the Tresca criterion is the limiting case of the two-parameter Coulomb-Moore criterion, which itself is only of its historical interest. And discussed, the Meson criterion is the limiting case of a viable, completely general modern future criterion. Drucker-Prager failure criteria. The Drucker-Prager theory was probably motivated by the desire of a general theory that would reduce to the Mises form in the limit, rather than the Tresca form. A course of action to accomplish this is quite direct. Simply replace the Coulomb-Moore six-side pyramid in principal stress space by a circular cone. Following this direction, write the possible failure as criterion as the equation of the top right, where Sij is the deviatonic stress tensor involved in a Mises criterion. But now the term and explicitly brings the mean normal stress effect, which is implicit in the Coulomb-Moore formalism. Parameters A and B are to be determined such that predicts an actual stresses failure at the tensile value T and the compressive value C. It is easily shown that this gives us the equation of a middle left. Finally, writing in terms of component gives the equation below that. As shown, only the positive sign is associated with the square roots in its principal stress space is that of a conical failure surface. The symmetry axis of the cone makes equal angles with the three principal axes. When T equals C, the failure surface becomes the circular cylindrical form of Mises. A simple example shows the inappropriateness of the Drucker-Prager criterion for representing materials failure. Take, for example, the case of cast iron, which has T divided by C equals 1 divided 3 value. Next, specify the condition of equal biaxial compressive stresses. Sigma 1 equals sigma 2 equals minus sigma, sigma 3 equals 0. Using this specification in gives, thus T divided by C is minor or equal to 1/3, allows unlimited compressive stresses. The Drucker-Prager criterion thus predicts that cast iron and all materials with T divided C minus or equal 1/3 will support unlimited stress magnitudes in equal biaxial compression. This, of course, is impossible. Looking the failure theory divided, this there predicts the failure stress in equal biaxial compression as 1.55 C for T divided C equals to 1/3. Clearly, the Drucker-Prager criterion is not suitable as a failure criterion for engineering materials. The general difficulties for the Drucker-Prager criterion, as well as with the following Coulomb-Moore criterion, are discussed in Christensen. Like the Coulomb-Moore form, the Drucker-Prager form receives attention and usage though not to as great extent. Coulomb-Moore failure criteria. The procedure for the Coulomb-Moore or Moore-Coulomb theory uses the Moore circle construction as shown in the figure in the left. On the normal stress sigma versus shear stress tau axis, plot the circles for unaxial tension and compression to failure as shown. Then two linear failure envelopes are taken as just being tangent to the two circles. In order to evaluate the safety for any given three-dimensional state of stress, the maximum and minimum principal stresses are used to form a circle on the plot. If this circle is inside the failure envelopes, then there is no failure. Otherwise, there is failure of the material. For example, take a state of simple shear stress. Form a circle with its center at the origin and just tangent to the failure envelopes. This circle intersects tau axis at the values of a shear stress failure S, given by S equals to Tc divided T plus C, as is shown in the slide, where T and C are the failure levels in axial tension and compression. The general characteristics of the construction are given by X equals t c divided c minus t, y 1 per 2, 1 divided 2, and square root of t multiplied c, and sin of sigma equals to c minus t divided c minus plus t. The procedure just outlined for failure assessment can be expressed in analytical form. Let sigma 1, sigma 2, and sigma 3 be the principal stresses, with sigma 1 being the largest and sigma 3 being the smallest, and in an algebraic sense. The failure criterion can be shown to be given by the equation of the bottom, but not the last one. And the first term shows the normal stress effect, and the second term as maximum shear stress effect. Relation directly reduced to sigma 1 divided by t minus sigma 3 divided by c minus or equal 1. This extremely simple form constitutes the entire two-property Coulomb-Moore failure criterion. In the limit of t equals c, the Coulomb-Moore form reduces to the maximum shear stress criterion of Tresca in principal stress space. This is given by the infinite cylinder of hexagonal cross-section. When t is minus c, the Coulomb-Moore form becomes a six-side pyramid in a principal stress space, and this six-side pyramid has but three-fold symmetry rather than six-fold symmetry. An analytical form for this criterion in terms of invariance has been given by Shachar, although it's far easier and to directly use the forms given here. The Coulomb-Moore theory has been used in applications as diverse as nano-indentation and large-scale geophysics. As with the Drucker-Prager example, it is not difficult to find realistic examples where the Coulomb-Moore criterion produces blatantly incorrect results. Some examples are as follows. Take a three-dimensional compressive stress state specified by sigma 1 equals to sigma 2 equals to minus sigma equals c equals sigma 3 equals minus 2 sigma. Substituting open parentheses minus 1 plus 2t divided c close parentheses multiplied by sigma minus or equal t. Thus, the Coulomb-Moore criterion asserts that materials such as brittle polymers and wide range of other materials can withstand unlimited compressive stresses in the stress state when T divided C is minus or equal 1 divided 2. The Coulomb-Moore form was very appealing in its simplicity of concept, and it presumed generally an ease of use. There was great enthusiasm for it in the early 1900s when it came into general use. Then it was shown by von Karman and V. Ucker to have considerable limitations for brittle materials, specifically natural minerals. Much effort has been expended over the years to correct and generalize this most simple and direct form of the Coulomb-Moore criterion, but to no special advantage of usefulness. It has continued to be used perhaps because of the perceived lack of a suitable two-property alternative, but nevertheless, the above examples unequivocally prove that the Coulomb-Moore theory is fundamentally incorrect and should never be used, even though it is widely disseminated and codified. Conclusions. Of the four standard and widely used failure criteria of isotropic materials, Mises, Tresca, Drucker, Prager, Coulomb-Moore, only the Mises criterion is of lasting significance. Although applicable only to very ductile materials, it is the classic result in that a specific application and it's very ductile and it surely will endure. As shown, the other three criteria fail to establish the credentials necessary for permanency and in fact can be misleading and patently incorrect in particular materials applications. Worst of all, none of the four can be used as general purpose failure criteria as they are completely inappropriate to the task. Furthermore, it is probably obvious that adding another parameter or two to the Coulomb-Moore or Drucker-Prager forms would be exceedingly unlikely to convert what is a completely unacceptable form into a transparently successful form. A totally new and fundamentally different approach it is clearly required. Although the results do not lead to any useful general failure forms, they do provide a hint of where to look for opportunity. In particular, the Coulomb-Moore criterion is completely linear in the stress components and is unacceptable. Other linear and quasi-linear forms, such as the Drucker-Prager criterion, are also unacceptable for the same reason. It is probable that the general failure theory would involve some nonlinear physical effects in some manner. Going even further, it is still conceivable that there could be a reasonably straightforward failure descriptor, but it is probably must have a non-linear formula to support it. And if the Mises criterion give any indication, this general non-linear formalism could be quadratic in nature. Thanks for your attention.